The next presentation is from Sofia Pechlivanidou. In the agenda is written from that she is coming from Norway. The meeting is dedicated to Mediterranean researchers and research. Sofia Pechlivanidou is a Greek. She's coming from Greece. And her research has taken place in Greece, but now she's working in Norway. And Sofia, we are very glad to have you with us today. And she will present a high-resolution records of interacting tectonics, climate, and sedimentation from the Corinth Rift. It's a study area in Greece.
Hello, everyone. Hello, everyone. Thank you very much. Thank you, Nikki. I would like to start as well by congratulating the organizers for this workshop. I'm very happy that I will present my work this particular day that we celebrate women's achievements worldwide. So thank you very much for the invitation. I'm a researcher at the University of Bergen, and my work mainly involves understanding the impact of tectonics and climate on surface processes within active rifts. Also, currently, I'm working on understanding controls on gravity flow sedimentation within deep water thin rift systems, such as the one you're looking here in the photo from the Corinth Rift in Greece. So my talk would be about the recent results from the IODB expedition in this rift, as I'm part of the science party for this expedition. Before I move on to the scientific part of my talk, I would like to acknowledge all the participants of this expedition. At this point, I think it's worth to mention that the chiefs of this expedition were both women, Donna Sillington and Lisa McNeil, and also half of the members of the science party were also women scientists. So Expedition 381 was an IODB mission-specific platform held late 2017 with the Fugro synergy that you are looking here in the photo. The onshore phase was on February 2018 at the University of Bremen at Marum. In total, 1,900 meters of cores were drilled with an 86% of overall recovery. And I have to say that this is a record in both coring and recovery for an IODB mission-specific platform. Drilling operations plus part of the analysis were done offshore. Here are some nice photos from the offshore phase. Whereas full core description, sampling, and measurements were done onshore at the University of Bremen at Marum. So for those of you who are not familiar with the Corinth Rift, I will just give a brief description of the area. The Corinth Rift is located in central Greece, and it is one of the most actively extending areas in the world. Rifting began further south and has migrated north into the Gulf at around 2 million years ago. Subsidence is mainly controlled by these north-dipping normal faults along southern rift margins. The Gulf itself has a maximum water depth of around 850 meters, and it is connected to the open sea through the Rion Strait to the west, where water depth is less than 60 meters. Therefore, during sea level falls, this connection was lost, and the Gulf was turning into an isolated lake. There are also other natural seals to the west and to the east that isolated the Gulf during past sea level falls. In the map also here you see the location of the 3 drilling sites of this expedition. 2 of them were drilled at the central part of the rift and 1 drilled at the eastern part of the rift in the Alkyonides Gulf. But the question is why to drill the Corinth Rift? And the answer to this is that the Corinth Rift is an ideal laboratory for understanding structural and surface processes during early stages of rifting. And this is because the Corinth Rift is a young rift with a relatively simple tectonic history and no overprint. It is a self-contained, rather small rift that allows us to characterize an entire tectonic and sedimentary rift system. It depicts a high strain rates. Extension rates reach up almost to 15 to 20 millimeters per year, especially at the western part of the rift. And also it has very high levels of seismicity. Furthermore, the high sedimentation rates that we observed within the Gulf allows us for a high temporal resolution. And finally, the thin rift stratigraphy, the last 2 million years, is well preserved offshore, where older faces are uplifted and preserved onshore, mainly along the southern rift margins. So previous studies in the area have shown that the thin rift succession below the Gulf is up to 2.5 kilometers thick, as you can see here in this seismic profile. Two main seismic stratigraphic units were observed, a lower transparent one that you see with gray color here in the figure, and an upper one that consists of alternating levels of low versus high amplitude reflectors. The cyclic alternation of these reflectors within this seismic unit 2 has been interpreted to represent marine and non-marine lithologies that were linked to glacier-static variations during the late Quaternary. So the low amplitude reflectors that you see with gray colors here are lacustrine sediments that were deposited during the glacial periods at sea level low stands, whereas the high amplitude reflectors that you see with black colors here are marine sediments that deposited during the interglacial periods at sea level high stands. However, deep sampling is needed to confirm the idea that I've just described and also to provide chronostratigraphy. So the scientific objective of this expedition was to obtain a high-resolution chronology for the thin rift sediments in order to address, first of all, the fault and rift structural evolution of an active continental rift. We want to understand how strain is distributed in time and space and the time scales of fault evolution at high temporal and spatial resolution. We also want to understand how a rift-controlled closed drainage system has evolved in time and space at high temporal resolution, 20 to 50,000 years, and also to unravel the relative roles of tectonics and climate on sediment fluxes. Secondary objectives, but still quite important, are the regional natural hazard assessment and the paleoclimatic and paleoenvironmental reconstruction of a semi-isolated basin during the Quaternary. Again, in the map here are the three drilling sites. The first one, site 78, at the central part of the Gulf, has recovered a condensed section from a horst block. You can see the horst block here in the seismic profile, and captured the upper most recent rift phase, seismic unit 2, and the lower older rift phase, seismic unit 1. Coring on this site reached 610 meters below seafloor. The second site, again from the central part of the Gulf, has recovered the most recent rift phase, seismic unit 2. Coring and logging on this site was down to 705 meters below seafloor. And finally, the third site in the Alkyonides Gulf has recovered both rift phases, and as you can see from the seismic profile, we reached the basement. Coring and logging was down to 534 meters below seafloor. So now we'll show you some of the lithostratigraphic and paleoenvironmental results that we got so far. These are the results from site 79 in the central rift. The results from the other central site are quite similar to this one. So I just choose to show you only the recovered expanded section. So from left to right, you are looking at the magnetic susceptibility with depth, macrofossil assemblages, bioturbation index, and sedimentary spaces that we define in Bergen. Based on this, we distinguish two main lithostratigraphic units, and a lower one that corresponds to the older rift phase and characterizes an isolated environment, and an upper one, unit 1, that corresponds to the recent rift phase and consists of alternating marine and non-marine sediments. Because stratigraphic variability within this unit is significant, this will be the focus of my talk for the next few slides. So bed scale stratigraphic analysis within unit 1 shown that most of the beds are really thin beds, less than 2 centimeters thick, whereas the thicker beds, the ones that are thicker than 25 centimeters, represent less than 0.7% in total. However, the most interesting result is that most of these beds are gravity flows that cover more than 60% of the total sedimentation. The rest is covered by the background sediments. These gravity flows show a great variety in terms of thicknesses, internal structure, and grain sizes. These are just two examples that you can see here from a gravity flow that has a coarse to medium sand base and shows a gradual grain size transition to the overlying mud. And another example from gravity flow that has a fine sand to silt base and shows an abrupt, rapid grain size transition to the overlying mud. The background sediments also show great variability in terms of bed characteristics. There are intervals where we have these bioturbated mud, silt, and sand beds, as you can see here from the core photo. In these intervals, bioturbation is intense, it's reaching 5 to 6, and usually these intervals have abundant marine and terrestrial microfossils that characterize a marine environment. On the other hand, there are intervals where we have more of these homogeneous mudbeds that alternate with laminated mudbeds. These intervals usually have moderate to abundant non-marine microfossils and characterize an isolated or lacustrine environment. Our age constraints show that the marine intervals have low sedimentation rates that range between 0.3 to 0.7 millimeters per year. Exception is the Holocene, where we have high sedimentation rates. In contrast, sedimentation rates within the isolated intervals are really high and reach up to 3 to 4 millimeters per year. Another interesting result is that the transitions between these environments, between the marine and the isolated, are usually marked by these white to light gray laminated mudbeds, as you can see here in the core photo. We've looked at this under ACN microscope, and we saw that most of these laminae consist of these aragonite needles that you see here in these photos. This is quite important because we can actually get age constraints from these aragonite deposits using uranium thorium dating techniques. The last site in the Alkyonides Gulf is similar to the central site, only on the upper part. So we have again alternating marine and non-marine sediments that overlie 100 meters of sediments that show an isolated environment. The difference in this site is that we've drilled almost 200 meters of these sandy conglomerates and reddish-brown sands with silt that show a more fluvial or alluvial fan depositional environment. At the bottom of the core, we've drilled this laminated buff-colored to greenish-gray silts that show a terrestrial or a lacustrine environment. At the bottom of the core, at 520 meters, we've drilled the basal conglomerates that probably correspond to the base of the basin. So what we've learned from what I've shown you can be summarized in these two paleo-environmental reconstructions for the marine and the isolated environments. Marine intervals correspond to sea level high stands when the Gulf was connected to the open sea. The observed low sediment supply within the Gulf is attributed to mixed forest on rift flanks that trap sediment. Exception is the Holocene, where we have high sedimentation rates. This is possibly due to anthropogenic effects in the last 6,000 years. During these intervals, the basin is underfilled, as it is today, where subsidence exceeding sedimentation. Marine microfossils dominate, and bioturbation in the sediments is high. On the other hand, the isolated intervals correspond to sea level low stands when the Gulf was isolated from the open sea. The observed increased sediment supply is attributed to the open grasslands on the rift flanks that drives high erosion rates. High sedimentation rates are almost 2 to 7 times the marine, actually. The basin during these intervals is again underfilled. However, non-marine microfossils dominate and bioturbation in the sediments is low. And now we'll show you some of the chronostratigraphic results that we got so far. Age constraints were based on different methods. We got ages from radiocarbon analysis on organic matter, forams, cells, gastropods, and ostracods. We also got ages from uranium thorium analysis of aragonite needles, from tephrochronology, from biostratigraphic markers such as the first and last occurrence of specific species, and from paleomagnetic data. In the slide here, you're looking at the chronostratigraphic correlation of the three drilling sites. These are the two central sites, and this is the site in the Archimedes Gulf to the east. What is worth to show you here is that Unit 1, that corresponds to the recent rift phase, is of Middle Pleistocene through recent age. Also, our ages show that the marine and the isolated intervals that have low and high sedimentation rates respectively correlate pretty well to the marine isotope stages, confirming the idea of sea level driven changes in basin paleoenvironment. Also, the transition, the rift phase transition, the transition between the Unit 1 and Unit 2 is of 700 to 800,000 years and is well defined by the Braches-Matsuyama magnetic reversal. And finally, by extrapolating the sedimentation rates, we got an age for the earliest seen rift sediments that it's about 2.5 to 2 million years ago. The last part of my talk will be about the structural evolution of the rift and what we've learned from this expedition. So we already know how rift deposenters within the Gulf evolved through time. These are some isochord maps illustrating deposenter development. These are from Nixon et al. 2016. During the early stages of rifting, sediments were deposited in two distinct 20 to 50 kilometers long deposenters that you see with bluish colors in this figure. However, from 700 to 8,000 years, a switch in rift polarity led to deposenter linkage and the formation of one single deposenter 80 kilometers long that you can see here with a purple color. However, drilling constrained chronology and velocity data from this expedition allows us to quantify fault activity with time. So we now know that the highest slip rates are at the central part of the rift, and this is because these faults that you can see here with red color form one long kinematically coherent border fault system. This is quite different from the short-term geodetic rates that show that the highest slip rates are at the western part of the rift. Another interesting result is by looking at the earthquake epicenters, the ones that are higher than 4.5 in magnitude. You can see them with these circles here. Most of these are concentrated at the western or the eastern part of the rift. However, little seismicity occurs at the central part of the rift, where we have the highest long-term slip rates. Having said that, and considering that these faults are linked in depth, we might expect that during a future earthquake event, many of these fault segments might rupture. Otherwise, this might mean that this part of the Gulf is deforming in a different way, that is seismically with fault creeping. So to summarize, this is the first sedimentary record of this length and this resolution in an active young rift. High-resolution stratigraphic analysis revealed major fluctuations in the basin paleoenvironments that are due to tectonic, sea level, and climate interactions. Our age model constrained the timing of the major rift phases. Also, our ages support sea level driven changes in basin paleoenvironment and constrained sediment accumulation rates. And finally, the integrated borehole and seismic data show that the highest slip rates are at the central part of the rift, as strain is localized on the border fault system that might have implications for earthquake hazard assessment. Thank you very much for your attention.
Thank you, Sofia Pechlivanidou, for this interesting presentation. Is anyone from the audience that I would like to ask a question? Nurit.
Yes, thank you, Sofia, for this great presentation. I have a question that is maybe related more to the tectonic framework of the Mediterranean, which bothers me for a time. I'm asking about the formation of the Gulf of Corinth, because the Mediterranean is subsiding under Europe, right? So how this elongated rift valley is explained, because I'd expect collision and pressure and push-up ridges rather than rifting and opening.
It's extension of the Balkan area, I would say. And there are other rifts as well, like the Spercheios Rift further to the north, and well, probably some more rifts that form due to this extension at the Balkan area.
There is also the Anatolian fault that is very active in the Aegean, and it's causing the rotation of Anatolia block, and as a consequence, it's also creating faults that are parallel with it or perpendicular secondary faults. And I guess this fault appeared as a consequence of Anatolia protruding in the Aegean.
Thank you. Thank you.
Any other question for Sofia Pechlivanidou?